All right, what we're wanting to do in today's lecture is we're wanting to describe that large empty space in an atom. We've already established that the atom consists of a small positively charged nucleus surrounded by a large empty space. And we know that within this large empty space, known as the electron cloud, our electrons are located. What we want to do in today's lecture is we want to describe the organization of the electron cloud. In other words, we want to take all the electrons in an atom and tell their probable location. The probable location of all the electrons in an atom is referred to as its electron configuration. Before we can talk about electron configurations, I need to define another term. We're going to talk about the electron configuration of atoms in the ground state. When we say an atom is in a ground state, all the electrons occupy the lowest possible energy arrangement. The story of electron configuration begins as a love story on the order of Cyclops and Jean Grey. Matter of fact, why don't you write down Cyclops? Write down Cyclops. C-Y-C-L-O-P-S. Cyclops. Our nucleus, with its positive charge, is really attracted to our electron with its negative charge. Our electron with its negative charge is really attracted to our nucleus with its positive charge. If you've ever been really super attracted to somebody and you guys are dating and it's the new relationship and you got that bad puppy love thing going, it takes all your energy not to spend every single moment with them. That's the same way it is for our electron and our nucleus. Our electron and our nucleus, to stay far apart, that requires a whole lot of energy. The closer they get together, the more of that energy they're releasing. There is a relationship between energy and probable distance the electron is from the nucleus. Therefore, the first way we divide up our electron cloud or group our electrons is on the basis of energy. We divide our atom into energy shells, or we can also call them energy levels. What we do is we take our nucleus here, and let's make our nucleus something fun here. Not something fun, just something easy to see. Alright, so we have our nucleus, and we'll define an area around it, and we'll call that area around it our first energy level. Then we have another area around it, and we'll call that area and that distance from the nucleus our second energy level. And then we'll have a third energy level. They gave me crayons. We have a third energy level. Then we'd have another energy level around that. That would be our fourth energy level. And we could even have yet another energy level around that one, and so forth and so on. And that would be our fifth. So what we do is we break the distance out from our nucleus into these energy shells. Remember, this is three-dimensional. The way to really think of it is like a Russian nesting doll. Right? You have your inner doll, then you have a doll around it, and a doll around it, and a doll around it. Well, in an atom, we name the first doll around the nucleus the first energy level, the second doll the second energy level, the third doll the third energy level. So we have energy levels going out from the nucleus. So the first way we organize the electron cloud is we divide it up into energy levels. Our energy levels are numbered or named using whole numbers. 1, 2, 3, 4, 5, 6, 7, and so forth. We also, when we want to talk about energy levels, use the symbol, the lowercase letter n. So if I'm talking about energy levels, I could say that the energy level can equal, or n can equal, 1, 2, 3, 4, 5, 6, 7, positive integers. And that as the value of n increases, two things happen, two trends that we can look at. First trend is the distance from the nucleus increases as n increases. The second trend is the size I'm having trouble spelling today. The size of the electron's probable location increases. In other words, the seventh energy level is much larger than the first energy level. The reason for that's really simple. We saw it in those high-tech illustrations I was drawing earlier. And in our analogy of the Russian nesting dolls, in order for an outer nesting doll to go around an inner nesting doll, it has to be larger. So as we move away from the nucleus, our energy levels have to become larger. Therefore, the number of electrons an energy level can hold also increases with distance from the nucleus. Each energy level can hold a different number of electrons. The number of electrons an energy level can hold the number of electrons in an energy level is equal to 2n squared. In other words, If I'm in my first energy level, I can have 2 times 1 squared, or 2 electrons in my energy level. If I'm in my second energy level, then I have 2 times 2 squared, or 8 electrons in my energy level. If I'm in my third energy level, I can have 2 times 3 squared, 9 or 18 electrons in my energy level. If I'm in my fourth energy level, I can have 2 times 4 squared, 16, 32, or 32 electrons, so forth and so on. So the number of electrons that can fit in a given energy level is 2 times n squared, where n, remember, is our universal symbol for an energy level. Okay, so that's the first way I can divide up that electron cloud, and I can tell you something about the probable location of an electron. Energy levels are subdivided. They're divided into sublevels, or subshells. And these subshells are divided into orbitals. Now, the orbitals are really what we're interested in. These orbitals are the probable location of a given electron. Before we talk about sublevels, we actually want to skip through those sublevels and talk really quickly about the orbitals. I know that sounds like putting the chicken before the horse. If you're upset about it, why don't you let out a banshee wail? Why don't you write down banshee? B-A-N-S-H-E-E, banshee, which I always found interesting that the X-Men chose to make banshee male, when traditionally in Irish folklore, banshees are generally female. But write down banshee. Alright, let's talk about orbitals. An orbital is the probable location of an electron. You should avoid the misconception of considering it a flight path. Early models of the atom, and some biologists, incorrectly state that electrons orbit the nucleus of the atom like planets orbiting the sun. And this was in fact the original model of the atom by Niels Bohr. However, that theory proved incorrect. The movement of electrons around the nucleus is much more complex. Depending on which class you have, we will or won't go into that more complex movement. What you should consider an orbital is where an electron likes to hang out. Back in the days before cell phones, if I wanted to find my friends on a Friday night, what I did is I got into my car, and I knew that my friends would be at the Dairy Queen, or the Court Square, or Walmart, or the school parking lot, or at the football stadium, or the student union. And what I would do is I'd pile in a car with a bunch of my friends, and we'd drive back and forth, checking the probable location for our other friends. I knew where my friends were likely to be, but I didn't know exactly where they would be, and because my friends were driving around looking for me at the same time, they were in constant movement, so where they were at any given moment was changing. However, I knew that they were very likely to be somewhere within that web of locations. So when we say the orbital for an atom, the orbital for an electron, what we're really doing is we're saying where that electron likes to hang out. and where, if we were to check at a given period in time, where we would likely to find that electron. Now, that leads to some interesting shapes. What we'll discover later on in this conversation is that orbitals aren't those boring circles. They're going to have some much more interesting shapes. But right now, you need to know that an orbital is the probable location of an electron. And electrons drive sports cars. So, an orbital can hold only 2 electrons. Just like the front seat of a sports car. All right, so let's go back to our big picture now. We said that we've had energy shells. And that we're dividing these energy shells into subshells. And these subshells are divided into orbitals. Now, our energy level tells us the energy of the electron. And the energy of the electron is related to the electron's distance from the nucleus. We divide these energy shells into sublevels. These sublevels tell us a couple things. First, the sublevel tells us more information about the energy the electron possesses. The subshell also tells us the shape of an electron's orbital. All right, so let's take a look here. The number of subshells in each energy level is different. And is equal to the number of the energy level or the energy shell. For example, that means here's our energy level. Number subshells. And we'll do names of subshells. Our first energy level has the number 1. Therefore, it can have only 1 subshell. The entire energy level is 1 subshell. We call the first subshell in any energy level S. And that's a cursive letter S. That's my cursive letter S. People think it looks like a 0. Let me do it a little bit bigger here. That's the cursive letter S. And there's another S, just so you can get used to my handwriting. Okay. So we have the first energy level can only have 1 subshell, so we call that subshell 1S, or the 1S subshell. Our second energy level, since it has a number of 2, can have 2 subshells. We call the first subshell in the second energy level the 2s. We call the second one the 2p. Whoops. The second subshell of any energy shell is called P. So we have the second energy level, 2 subshells, and we call them the 2s and the 2p. Our third energy level, because it's the third, can have 3 subshells. We call the first subshell in the third energy level the 3s. We call the next one the 3p, and the next one the 3d. And you guessed it, we call the third energy level the third subshell of any energy level, of any energy shell, is called D. So that would be the 3D. 3D, that's awesome, isn't it? I'm putting on my glasses now. I guess you can't really see me moving the iPad back and forth in front of my face, can you? Well, move your head back and forth in front of the screen so you're simulating 3D effects. Our fourth energy level would have 4 subshells. We'd call the first one the 4s, the next one the 4p, the next one the 4d, and the last one the 4f. The fourth subshell of any energy level is called the F subshell. It should be noted in nature It should be noted in nature, no element has a subshell higher than the F subshell occupied in its ground state. Therefore, any subshell we talk about after F exists simply as a theoretical construct. Say that one 10 times fast. All right, but let's do one more here. We come to our fifth energy level. It's going to have 5 subshells. The first subshell in the 5 is the 5s. Then we have the 5p. Then we have the 5d. Then we have the 5f. And after F, it's alphabetical. So it's going to be E, F, G. So it would be the 5G. However, it should be noted the 5G is a theoretical construct and not occupied in the ground state of any atom. All right, so we have energy levels. They're divided into subshells. We call these subshells, and the number of subshells in an energy level is equal to the number of the energy level. we always name them S, P, D, and F in that order. And what do they tell us? Good question. Let's talk about these mysterious different subshells. The S subshell has one orbital. And since it has one orbital, that means it can hold only 2 electrons. The shape of the s orbital is the most boring of the orbital shapes. It's a sphere. The probable location of an electron in an s orbital is a sphere around the nucleus. So all your s orbitals will be spherical in nature. The p orbital, the p subshell, every p subshell contains 3 orbitals. And if an orbital holds 2 electrons each, then a p orbital can hold 6 electrons. Now, the p orbitals are really, really neat. The p orbitals have what I call a 2 ice cream cone shape. It looks like 2 teardrops, and in the middle there, you have your nucleus. Bow ties are cool. Now we just need a fez. It's Dr. Electron. Alright, I amused myself, and that's all that matters. Our p orbitals are this ice cream cone shape. This ice cream cone shape in 3 dimensions can be thought of almost as a line. And you can turn these 2 ice cream cones so that they lie along a x-axis. You can turn them so that they go along a z-axis, or you can turn them so that they go along, and here's where my artwork's really challenged, a y-axis. Because you can turn this shape 3 different ways, that means you can have 3 different p orbitals, all with the same shape, but with different 3-dimensional orientations in space. Depending on what class you're taking, you'll go more into the orientation of those p orbitals. But at the moment, you just need to know that the p orbitals look like 2 ice cream cones that don't touch in the middle, and the nucleus is right there in the middle where they're not touching. So you have 3 p orbitals, each holding 2 electrons for a total of 6. Then you have D, and it has 5 orbitals. And if each orbital can hold 2 electrons, then the D subshell can hold 10 electrons. Now, the D orbitals, they're really funky in terms of their shape. You have 5 orbitals. 4 of the orbitals will form a 4-leaf clover, or a 4-leaf clover made out of 4 ice cream cones. I'm not very good with my ice cream cones at the moment here. Don't think that's any better. But 4 of the orbitals will have this ice cream cone shape, again with the nucleus in the middle, and you can tilt that so that it lies between your XYZ plane. But 4 of these 5 orbitals will have this shape. One of the d orbitals has what I call the Homer-Simpson special. Jelly donuts. Because Homer Simpson just doesn't want 2 ice cream cones. He wants 2 ice cream cones with a jelly donut shape in the middle. So those are the shapes of the d orbitals. The shapes of the f orbitals are beyond the scope of this lecture and my artistic ability, but basically you're looking at an even more multi-lobed ice cream cone shape. Your F has, guess how many orbitals? Anybody seeing a pattern so far? 1 orbital, 3 orbitals, 5 orbitals. 1 plus 2 is 3, 3 plus 2 is 5, 5 plus 2 is 7. So your F has 7 orbitals, and if you had a G, it would hold 9 orbitals, right? Keep that plus 2 sequence going. But you have 7 orbitals times 2 electrons each. So your F orbitals hold, your F subshell holds 14 electrons. So, your subshells tell you shape, and they tell you the number of orbitals in their given region, and they tell you a little bit more about energy, and thus a little bit more about distance from the nucleus. Energy increases going from the s orbital to the f orbital. Matter of fact, let me write that in a way that makes it a little prettier. S, P, D, F. Energy increases as you go from S to F, and therefore your average distance from the nucleus also increases a little, but it's more important to pay attention to that energy difference. Energy increases from S to F. So now we know our organization of our electron cloud. Let's take a look at the big picture. I'm going to draw what's known as an orbital diagram, and different books like to do these orbital diagrams different ways. Some like to draw boxes, some like to draw circles, some like to draw lines. I'm a line person myself, but all orbital diagrams, which is what we're going to use to illustrate the electron cloud, has energy increasing this way, and therefore distance, relative distance from the nucleus increasing. In my orbital here, I think I'll actually use boxes. I think boxes are a good idea here. I'm going to draw a box, and this each box I draw is going to represent 1 orbital. The first orbital, or the orbital with the lowest energy, is in the first energy level, right? That makes sense. And the first subshell in that first energy level is the S, and it has 1 orbital. The second orbital I find is in the second energy level, and it's in the S subshell as well, so it's in the 2s subshell. But I have 2 subshells because I'm in the second energy level. So with a slightly higher energy, I have 3 orbitals belonging to the 2p subshell. I hope you're following with me here. This box represents a 1s orbital. This box represents a 2s orbital. And remember from our previous discussions, and if you glance back at your notes, that our 2p has 1, 2, 3 orbitals. Then we climb in our energy. The next energy level we come to is the third energy level, and it has a S subshell, it has a P subshell, with 3 orbitals, and then with even higher energy here, and it's not going to let me erase that. Maybe it let me shrink. Ooh, I can't shrink the. Whoa! Did I make people seasick? I'm sorry if I did. Then I'm in the third energy level, so I have 3 subshells, right? So I have a 3D subshell, and remember it has 1, 2, 3, 4, 1, 2, 3, 4, 5 orbitals in it, with higher energy than the 3p. So that's basically what we've done. We've divided that electron cloud, or organized that electron cloud on the basis of energy, into orbitals. Those orbitals represent the probable location of finding electrons. We group these orbitals on the basis of their energy into energy levels and subshells. This is a lot of memorization, but don't worry, the periodic table is going to help us through it, and that's the subject of your next lecture. Before we go to that next lecture, though, write down Nightcrawler. Write down Nightcrawler. Everybody write down Nightcrawler. Hope you wrote down Nightcrawler.